Okay, we're recording. Let's do a quick recap actually. Start off a bit since it's been a week. Um, so, for this section, what we focused on is idealization. So, how to go from a real life structure, which is basically ribs, stiffeners, a skin panel, and multiple sections. How you can analyze that. And we said, like, okay, we can dumb it down basically to say that the skin only carries shear, no normal stresses, and sparse and the stiffness they carry the normal direction, the direct stresses. So and to basically to make an analysis approach, we said, okay, well, we're gonna lump the masses of say of the stiffener and the section of the skin into one section, and that makes it basically our life a bit easier in analyzing it. And we said like because we assume that the skin doesn't carry any shear stresses, the variation of the shear stress along the skin does not change what it normally does. So the only time that the shear stress changes is, or shear flow changes in this case, is when we pass a boom. And a boom was one of those lumps of mass. So that's what we basically start off with. We came up with an equation by analyzing the real structure, which is, again, has variation of direct stresses along the skin panel. And we said we're going to replace that by two booms that carry all the direct stresses and a skin that's basically zero. And then based on that, we could do a moment equilibrium equation. And we know that those two must be equal in the real life case and in the idealized case. And based on that, we could come up with an equation for the first boom area. And then we did repeat the same thing, but we didn't look at the total forces. We did the same thing. We did an equilibrium equation on both sides. We set them equal, and then we basically have our second equation for the boom area. And we know that the boom area is basically a function of the skin, the width of your between the two booms, and then the ratio of sigma 1 and sigma 2. And that's the stresses in the boom 1 and boom 2. And we also said, like, well, we know from our experience or direct stress equation is that sigma 1 and sigma 2 are a function of the moment of inertia, and the y distance. Y being the distance from the central axis to the location where you want to calculate your direct stresses. Because the moment and the moment of inertia don't change for either booms, you can cancel those out, and basically this becomes equivalent to the distance from the centroidal axis. So sigma 1 and sigma 2 becomes basically y1 and y2. So we did a quick example where we had an wind box, and we calculated the boom areas of 1, 2, 3, 4, 5, and 6. Of course, based on symmetry, we say the 1 and 6 are equal, 2 and 5 are equal, and 3 and 4 are equal. And then we calculated all the boom areas. Catch was, make sure you use the correct thicknesses, the correct distances, and also you add the area of the stiffness to it. So this lump, you start basically with that plus the equation that we derived earlier for the boom areas. And as last, what we said, okay, if you looked at the equation again of our direct stresses, we said the moment of the applied moment don't change because that's just an applied given force. The x and y location, that's basically the location with respect to the centroid. They don't change if we have a real structure or an idealized structure. So the only thing that changes is basically the moment of inertia. And the moment of inertia changes because we assume that the thickness of the skin is 0. So every time we add an 1 over 12 h cubed t, it will be equal to 0 because we assume t to be equal to 0. So basically what it does is when we do an idealization, the moment of inertia is simplified to only the standard terms. And that's what we see here. And then we looked at the shear flow equation, similar aspect of it. The only difference is in this case is we can assume that the skin carries sometimes a normal stress component to it, and or we can assume it doesn't carry any normal stress component to it. If we assume that the skin is only effective in shear and not effective in normal stresses, then the TD, the integral part, basically drops out. This T becomes 0, so you can drop out, and the moment of the shear flow is affected every time when we pass a boom. And we did a quick example, and then you can assume that the real structure, the non-idealized structure, what we did, and I said topic 2, after when we did in a shear flow topic, you can do the normal one without idealized sections, and then you can do the idealized section, and you can see what the differences are, and then you can increase the number of booms to get it within 5% of the analytical value, which would be the real structure. So with that said, basically I left this problem open on the board and basically ask you guys to do it. And this is actually example 20.4 from the book. And we're going to do this together. And this will be a good basically bridge to the next topic, will be multi-section of shear flows. So let me see. Yeah. Okay. So let's draw a figure. Symmetric cross section with a load of 10 kilonewton applied here. Let's call the numbers as well. 1, 2, 3, 4, 5, 6, 7, 8. We have given the shear force. So Sy is equal to 10 kilonewton. And we are given the booms areas. So of course symmetry, so 1 and 8 are equal, those are equal to 200. We have 2 and 7 equal. We have 3 and 6 equal. And we have 4 and 5 equal. We have 250, 400, and 100. So, of course, we have one axis of symmetry. So, our shear flow equation basically reduces, so we can write that as well. 3S is equal to minus Sy, Ixx, and then we assume skin is only effective in shear. So this means that TB is equal to 0. So the integral part will drop out. Yes?
I have an appointment to go to. Is there anything that will go over today that I can't just review in the video later?
No, you can basically review it on the,
Thank you.
no worries. So the only topic we're going to discuss later today is we're going to do the shear flow problem because it's a nice bridge to go to multi-section shear flow. So if you have any questions, just email me. Okay. So our equation basically reduces to minus Sy Ixx, and then the summation of the booms. And of course, since this is a closed section, so we have our correction shear flow as well. So, okay, if we look at this problem, a couple of things should immediately rise up. This is a boom problem. So your moment of inertia will be determined by basically the standard terms only. Ooh, they have a camera. It's over there. Fancy. That's for later. Okay. So what I said. Okay. So we see a problem like this, and this based on experience what past years have happened. People tend to overcomplicate things. What they do is they don't realize there's an idealization problem, so they still use the Ixx of 1 over 12 b cubed t, and for some reason they add the this part to it. So you're just overcomplicating it. Since this is an idealization, and every time when you basically have lumps of mass, some boom areas, you should basically know that the moment of inertia will only be the Steiner terms. So note to self, Ixx will be given by only the Steiner terms, or the moment of inertia given by the boom theory. This is also on the formula sheet, so should not be difficult. And the second thing which you have to realize, this is a closed section. So therefore, make a cut, solve the open section, solve open section, solve for correction shear flow, add all Q's. So that immediately should pop up in your mind. And then from here, what you can do is you just take the boxes. Since the moment of inertia is basically independent of where you take the cut, you can just do that one first. But you can also just start off by making a cut. We're gonna follow how Maxon is doing it, and the reason why I pull up this problem is in Maxon he does a weird trick without explaining it. So in Maxon he does make a cut here. So let's continue. Our cut is at 2, 3. So what does this mean? So we know from our shear flow equation with boom theory is that the shear flow only changes when we pass a boom. We know because we made a cut here that the shear flow at this location will be 0. So this means that this whole shear flow in this section 2, 3 is 0. Because we don't pass a boom, therefore it does not change. By symmetry, we know that this shear flow is equal to 0 as well. 6, 7. And this is for the open section. So we made a cut, it's open. So that's already what we analyzed by just looking at the problem and by taking a moment and analyzing what the problem is and what we have to do. So now let's start solving it. So first what we have to do is find the moment of inertia. So let's find the moment of inertia. Let me see a good location to. Let's do it here, and then we do the shear flows on that side. So moment of inertia. We know that's the boom areas multiplied by the y distance squared. So, of course, we need the distances. This is 100. Let me draw a bit closer so it's on the screen. And this is 100. This distance, that's 200. We have this distance is 120. This distance is 240. This distance is 240, and this distance is 60. What we also know is by looking at a problem, since it's symmetric, central will lie somewhere on this axis of symmetry. So centroid C on axis of symmetry. And that's important because we're now looking at the y distance, so we don't have to calculate the centroid because we already know it lies on this axis, so we just are interested in the y distance. So we don't have to calculate the centroid location because the x distance will not play a role in either this equation or this equation. So we save ourselves a step. So now let's do it. We can use symmetry, so we can just do the top half and then multiply by 2. So let's do that. 2 times and then summation of by squared. So let's start off by 1. So that's 1 is 200. The y distance is 60 between 1 and 8. So y distance is 30. So 30 squared plus 2 is 250. And this distance is 200. So it's 100 squared from the centroidal axis plus 3 is 400. And that lies on the same height, so that's 100 squared as well. And then we have B4, B4, which is this one is B4, which is 100 and then 50 squared. That's 100 times 50 squared. And then the 2 take care the bottom half. And if you calculate that, we get 13.86 10 to the power of 6 millimeters to the power of 4. So we can also do is, this is 10 kilonewtons, so that's 10 to the power of 3 Newton. So in these kind of problems, since we have two numbers, let's just calculate what this ratio is and continue with that. It's just making it a bit easier. So when we calculate basically Sy over Ixx, we get our shear flow equations. As like I said, let's start here. So let's do Q is minus Sy over Ixx, and then since we have an open section, the QS0 is currently 0. So this is our open section because we made a cut. So let's fill in the numbers. So this is minus 10 to the power of 3 over 13.86 10 to the power of 6 summation pi yi, and this is equal to negative 7.22 10 to the power of minus 4 pi yi. So we're going to continue doing this. And now we're going to start our shear flow equations of an open section. So what we said earlier, we said that P23 is equal to 0. So we can already start. QB, since we made a cut, 2, 3, that's equal to 0. Because we don't pass a boom along 2, 3, and we start with a cut, it will be 0. Okay, then we can go from, let's go from 2 to 3, and then 3 to 4. So we go to QB 3, 4. So of course, at this point with 0, so the starting point is 0. So we add negative 7.22, 10 to the minus 4, and then the summation of booms. So we pass only one boom, that's basically boom 3. So that's 400. So that's 400 multiplied by y. Y in this case was 200, so half of it is 100. So 400 times 100. So that's equal to negative 28.9 Newton per millimeter. And then we go to QB45. So at this location, let's draw it in. We have negative 28.9. And now we calculate 4 to 5. And when we go from 4 to 5, we pass boom 4. So we start at negative 28.9 and minus 7.22, 10 to the power minus 4. And we pass boom 4, so boom 4, that's equal to 100. The y distance is equal to 50 plus. So it's also important in this case, the sign of y does matter because we have a singular y. So it's no squared, so there's no cancellation of signs. So it's multiplied by 50. And if you add this up, we get negative 32.5. Go back, we draw this, negative 32.5. Immediately, per definition, since we have symmetry, we can calculate 5, 6, then we pass 5. So let's do that actually. So we get QB 5, 6. There's 32.5 minus 7.22, 10 to the power minus 4. The boom area is 100, but the y distance is negative 50. So basically, you end up again with 28 or negative 28.9. Newton millimeter. So here, negative 28.9. Did we have to do this? No, because we can assume symmetry and immediately know that 3,4 is equal to 5,6. Yes?
So if we hadn't have noticed that the sign change wouldn't have happened, and we got like 28.9, should that have been like a thing that we would have noticed like on that?
Yeah. Yeah. Because the symmetry, say for example, if you did this incorrectly and you had 50, so this negative number, this is negative, and this would be a positive, so you would get like, 30, 33.6, so 3 at 0.1, yeah, you get 36.1. So you get negative 36.1, and by default, that would be no longer symmetric, and then you would notice there's something wrong. And then this, you should have corrected this negative 50. Because now it becomes negative and negative, so you add up again.
So if you're doing it correctly, 3 and 4 should be the same as 5 and 6 because of symmetry?
Yeah. And then, of course, we already noticed from symmetry that 6, 7 is equal to 2, 3. We can calculate that as well. So you can do QB 6, 7, and you should know that you get negative 28.9 minus 7.22, 10, and this is 10 to the minus 4, and then 400 multiplied by minus 100, and that should be 0. And you also notice that this is symmetric, except with the 9 side, so this portion, except from the starting numbers. So what you basically added a negative number, now you add in positivity. So you would also see that in your equations. And that will be equal to 0. So now you have a choice. You can basically continue from 0 to 6, 7, 8, and then 8, 1. I'm going to follow Maxon. What he does, he restarts basically. And the reason is because it's symmetric. He says, okay, I go to the left, I get my numbers. I go to the right, I get my numbers. It's an option. The only thing that changes, if you would continue from this side, you assume that this goes basically up. You just have to make sure that at the end, when you have negative numbers, the correct shear flow is, the shear flow is going in the correct direction. Okay, so let's see. We're going to restart at 2. So we're going to do QB at 2, 1. Also, again, I think I've mentioned this before, but the numbering indicates the directionality. So if you say QB here, 3, 4 is negative 28, I assume that negative 28 goes into this direction. But if we have said Q4, 3 is negative 28, that would be incorrect, because it should be positive. Because the negative sign only indicates directionality. So we assumed in this direction, and therefore it's negative. So in theory or in practice, it actually goes in the opposite direction with the same value, magnitude. So again, we do 2, 1. So we start at 0, so we get negative 0.722, 10 to the minus 4. And then B2, B2, that's 250. Yeah, 250. And then multiply by 100, because that's distance. And then we get negative 18.1 Newton millimeter. So we get here negative 18.1, and then we do 1/8. QB 1/8, negative 18.1, that's our start value, minus 7.22, 10 to the minus 4. We pass 1, so that's 200. That's 200 multiplied by 30. That's the y distance. And then we get negative 0.22.4 Newton millimeter. And we get here negative 22.4. And by definition, this should be negative 18.1. So we have now calculated all our open shear flow sections. So keep this in mind. This is the open shear flow. So the next step is calculating our correction shear flow, and we did that by moment equivalence equation. Yes.
Professor, is there a way to just look at the problem and then intuitively speaking have a rough idea where should the maximum shear flow should be, or is it like we have to calculate it for all the sections?
No, you know, by definition, we'll lay somewhere, in this case, it's metric, and we have a vertical axis, shear force. So we'll lay on this side or that side, and by definition, since this is slightly bigger, and your boom areas of 4 and 5 are bigger than 1 and 8, so the maximum will lay on this side. You don't know the value, but you will probably predict that, because the maximum will correspond with a centroidal axis.
I'm asking this when you're doing the calculations, it's actually double checks that, okay, so.
Yeah. So you can theorize that the maximum will lie somewhere here. And you can calculate that if you want to.
So since the direction and the sign of the shear flow, are directly involved with each other, how do we know that the shear flow from 8 to 7 is the same as 2 to 1, but just the opposite direction?
Because you start on this direction, so we assume 1 to 2, so we're gonna go from this direction, and then we went 1 to 8, and then 8 to 7 should be in that direction. So you just follow the directionality around the clock. Say, for example, if you had calculated here and it went up, then this would be 18.1, this would be 22.4, and that should be 18.1. But because we restarted at the top and went from 2 to 1, that means that shear flow is going that direction.
But all those are negative, so it's actually going the other way.
Yeah. So let's see. We did this. We solved the open section. So now we have to solve for the correction shear flow. So for the correction shear flow, I'm gonna delete this part to have more room. So we have the So we didn't basically moment equivalence equation. And we said that on one side we have the shear force multiplied by our distance to our moment location is equal to the integral of all the QBs multiplied by the arm P ds plus 2 times the enclosed area of QS0. So those are generic equations. So now we have to basically determine the moment arm around the given section. So we're going to calculate, if we draw a line here, we're going to calculate the moments around this point, and let's call that O. So we're going to do a moment equivalence equation around point O. And the reason why we choose that is we have the shear force going through that section, so there's no moment arm, so this part is equal to 0. So it simplifies our life a bit. And in this case, now we have to find where the moment arm is for each of these sections. And we multiply the section by the shear flow by the moment arm and the length of that section. Okay, so we said this is equal to 0. Now let's start with locations that are simple. One more thing. We have to also define a correction shear flow. So let's assume, let's see what Maxon did. I didn't identify. Let's assume it's in the same directionality. So QS is going this way. Okay. Because this will add if the moment is positive or negative, right? So let's start off with the easy parts. So we know that this distance from 0 to 4, 5 is 120. So we can start with this one. So it's negative. Let's see. No, 0. Okay. Let's assume counterclockwise positive. So we get this is negative, right? So it's it's going to be positive if we draw it like this. So we still have to use the negative sign. 32.5 multiplied by the length, which is 100, multiplied by the arm, so that's 120. So a side note, normally we had this, right? QB PDS, right? And normally the shear flow would change with length along the segment. But in this case, the shear flow, because there's no booms here, it's constant within the booms. So this QB is a constant. The moment arm does not change with the location, so that's a constant, so we can P out, and so we get this, ds. And if you evaluate this integral, it becomes QS moment arm PS. So that's the reason we just multiply it by the length of the segment. Okay? So that's side note.
Where's the 120 come from again?
That's this moment, this arm.
Okay.
So that's the moment arm. So now let's do 1/8. So this is QB 4/5, and then 1/8. So 1/8 goes down, so that basically creates a clockwise moment. We assume counterclockwise to be positive, so this is negative. So negative, again, negative 22.4, multiplied by 60, that's the distance, and the moment arm is 240 plus 240 is 480. 6 and 7 are 0, 2 and 3 are 0, so it leaves us with 3, 4, 5, 6, 7, 8, and 2, 1. And there's a reason why I did these two first. So this is QB, let me see, we calculated 1/8, right? Because now what Maxon does, he does a trick without explaining it. So what he does is, he said, well, if I have a constant shear flow, it's basically like torsion. And the moment around the point with torsion, we said, is equal to, the torque is equal to 2 times the enclosed area times the shear flow. And this was a constant, and we said that torsion created a constant shear flow. Now we have a constant shear flow, and I want a moment around the point O. So how I can calculate that is by using this principle as well. So he calculates the contributing moment from 5, 6, 7, 8, and of course 1, 2, and 3, 4 by using this principle without explaining it. And he says like, I'm just going to calculate what this area is for 5, 6. So if you add 5, 6, it's again counterclockwise, so it's plus 5, 6, which is a negative number, so 28.9 multiplied by 2 times that area, so 2 is easy. And how do I calculate this area? You can use the cross product. So if you now transform 5 and 6 to points in a coordinate system, so we have our point O, we have point 5, we have point 6, and this is a point O. Let's come up with a coordinate system of 5, 6. And we start with this is our central axis. So this is negative 120 and negative 50. So x is negative 120, comma, negative 50. And 6 is x is 0 and y is negative 100. So 0, comma, 1, negative 100. So those are our coordinates with respect to point O. So the area in this case will be the cross product of point 1, R1 cross R2. That will be our area. And the cross product is nothing more than, so if you negative 120, negative 50, 0, 120, 100. So 120 minus 120 multiplied by minus 100 minus negative 50 minus, multiplied by 0. So in this case, the area is negative 120 multiplied by negative 100 minus negative 50 multiplied by 0. So the area is 120, 12,000 in this case. So we add 2 times, and the enclosed area was 120 multiplied by 100. And we take out negative signs. Okay? And the reason why I say this, explain this a bit more detail, is he uses this, but he doesn't tell you what he used. So it can be a bit odd that here he uses basically moment arm and length traveled, and here he uses basically area without explaining it. So it might be confusing to you that, especially since this is 120, that you think he uses this moment arm at 0.5, for example, because he says he goes from 5 to 6. So just be careful with that.
What does it say that, let's say, negative 50 times?
0, because the x-coordinate was 0.
So then he just does that for all the other links.
He does that also for 7, 8, and we can do that as well. So 7, 8, it goes negative side. So it's a negative number here, negative minus 18.81, and then 2 times, and then again, he does the same thing. So let's draw the coordinates again. And I advise you not to do this on yourself. See if you get the same number as I do, okay? Because this can be somewhat tricky in some cases. So I'll do it as well. And in the meantime, do it for yourself. So we have 0.0 here, we have 0.8, we have 0.7, and then we just write down the coordinates. So this is negative, or the plus 240, so the x-coordinate, and negative 100, and this coordinate is plus 480, negative 30. So the cross product will be 240 multiplied by 480, no, 240 multiplied by negative 30. Yeah, let me see, I always mess up as well. So 480 and negative 30, so 240 multiplied by negative 30 minus 100 multiplied by 480. So this becomes a plus. So you get basically 480 times 100 minus 240 times 30.
So when you're writing the coordinates, did you change your reference axis?
No, I still kept it the same because that's the reference axis with respect to the location you take the moment from, around. So it's always with respect to the where you take the moment. Yeah, and this is 240, so you know that x coordinate of 7 is 240. We know that this distance is 200, so from this distance, from 0 to 7, the vertical distance, negative 100. So that's 240, negative 100, x, y, x, y. So this is x, y, r1, r2. And then you do the cross product. So, and this is now, especially in this one, is a tricky point. So what Maxon does, he has this, value 480 multiplied by 100 minus 240 multiplied by negative 30, right? If we transport the negative, so we get in the minus here. So what he does is the following. He says, well, this is the same as 2 times 240 multiplied by 100 minus 240 multiplied, or minus, 240 multiplied by 30. So that's the same as 240, 2 times 240 multiplied by 70, because now I can take that out. So this is 480 multiplied by 70. So you can see that this is somewhat confusing. If he just gives you this number, you have no idea where it comes from. Actually, yeah. Even worse, he does this step. He says this is 2 times 240 multiplied by 100 minus 240 multiplied by 30. So this is 240 multiplied by 100 plus 240. Let me see. Yeah. It's 240 plus 70.
How mean way does that make it simpler?
I don't know, but this is what he does, and he does it a couple of times, and this is one of the examples that it doesn't make sense at all. But the key point is he uses the area, and for the area to calculate that in booms, since it's a constant shear flow, and constant shear flow basically gives us a torque, which is basically in plane moment, we can use the area as well. That's the key point of it. And then for the area to calculate it from a complex shape, we've known where the moment arm is not clear and the section where it travels over is not clear, then the cross products is very simple to do.
But like for simpler shapes, let's say we're solving for 6 and 7, then it would just be half the base and the height, that's it.
Yeah, that would be just basically 240 times whatever this height is, that's 100.
Okay.
Yeah. And then of course, so I'm gonna leave this as is, like here. So this was a negative, and then we add, since we said constant shear flow goes counterclockwise, so it's a positive number, and then you can calculate based on just geometry what the total area is. I will give that to you as 97. So 2 times 97,200 plus QS0. And now you have one equation, one unknown, you can solve for QS0. And if you solve for QS0, so QS0 in this case becomes negative 5.4 Newton per millimeter. And then you can basically add this to those values. So what you can do is now, once you have this, flip all the signs so it goes in the right direction, and you make sure that you have the correct signage.
Could you note which QBs those are?
Oh yeah, so this is QB 5, 6. This is QB what you said, 7, 8.
For 7, 8, is it should be negative or positive? And
Yeah, I should have done. Let's call this 8, 7. In this case, it will work out, but then we can keep that negative number in. So that's 8, 7. And then of course, this must be multiplied by 2. So twice, because symmetry, so you get 1, 2, and 3, 4 as well.
And the bottom one?
This is the correction shear flow.
Where's
So-
that area come from though?
Oh, you can calculate that because it's basically triangles and rectangles.
Oh, okay.
So you can just calculate that. You can calculate this section. So you split it up in triangles and rectangles and you calculate it. And then you have your correction shear flow, and then you can basically add that to your shear flows. So in this case, let me see. Yeah, so since this is a negative number, okay, let's do some redrawing. So we're gonna delete all the arrows. Okay. Since they were all negative, we assume that they're gonna be positive, so we know that this was like this. This is our official version, right? This was like this, then this is up, and this is up. This was also negative, so correction shear flow goes not counterclockwise, but clockwise. So this goes like this. So now we add this to it. So we add all the correction shear flows here, 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 and there. So now everything is in a positive direction, and now we can just add them together. So we know that where they match in sign, they will be added, and where they match and where they opposite in sign, they will be subtracted. So our final shear flows, let's use thread for that. So let's start with QS 2.1. 2.1, that's 18.1 minus 5.7, 5.4. That is negative, oh no, 12.5, 12.7. And 12.7 goes to that direction. And we do the same thing. So for QB, and to be fully correct, so QS should be 1, 2. Since we're going into this direction, so that's a positive number. Q81, that's negative, oh, that's 22.4 minus 5.4, that's 17. Yeah, 17. 6.7 is just 5.4. So QB, QS 7.6 is just 5.4. And then 5.6, QS. Let's write it. Sorry for the mess. So QS 5.6, that's 28.9, goes in the same direction, so we add 5.4 to it. So we get 29.3 plus 5, 34.3. And then QS 5.4, so this is 6.5, sorry. This is 5.4, so that's 32.5 plus 5.4, that's 37.9. And then 4.3 is the same as 6.5. So that's how you would solve it.
Could you explain again when why do we subtract and when do we add the correction shear flow?
So I'm gonna basically redraw this in a bigger format, hopefully to be a bit more clear. So this is our problem. Okay, so this was our problem. And we calculated all the correction shear flows. And they were negative numbers, right? So based on that, we know it's positive. So when we calculated here, we said 3.4 is negative 28. So let's add numbers, 3, 4, 5, 6, 7, 8, 1, and 2. We said 3, 4 is 28.9. So going from 3 to 4 is negative 28.9. So we know by definition it goes this direction, 28.9. We said 2, 3 is 0. So let's call this 2, 3. So this is 0, so it doesn't matter. So it's just 0. Put a 0 there. This was 0. We calculated 2, 1 was negative 18. So we know that 2, 1 goes in the opposite direction. So it's 18.1. We calculated 8, 1. So we go downwards, negative. So this goes up positive as well. And this is 22.4. We calculated, 2, 1 is same as 7, 8. So this one goes like this, 18.1. This is 0. This will go in this direction, 28.9. And we calculated 4, 5 was negative 32. Because negative, it goes up with 32.5, right? So that's basically what we did is now we redrew the Shear flows, and then every time when we saw a negative sign, we flipped the directionality. We also said in the beginning, we assumed the correction shear flow to be counterclockwise. But that was a negative number as well. So the shear flow goes clockwise. So the shear flow goes in this direction. Let's draw that on the inside. Because we got a negative number, and we assumed counterclockwise, so it goes clockwise.
Wouldn't that be the other direction?
Yeah. So it goes this direction. Right? Now we can just match it. So this is 5.4, this is 5.4, this is 5.4, 5.4 here, 5.4 here, 5.4, 5.4, 5.4. So here they go in the same direction, so they added here. This was 0, so it remains the same. Here they go opposite direction, so you subtract it. Here they go opposite direction, so you subtract it. Here they go opposite direction, so you subtract it. Here it's 0, so it goes the same directionality. Here you add it again. So that's how you do it. What you could also do is keep the negative numbers and keep 2s also as a negative number, and you get up the final solution.
I'll take the positive.
Yeah. So it just, as long as you remain consistent, it will not make any difference in the final answer. And of course, your final answer would be making sure here, so answer the question. So in an exam, you would get points for this, the cut, solving the open shear flow, solving the correction shear flow, and also you get points for actually adding the shear flows together. So don't forget this step. Just drawing it like this is not sufficient. Say it, okay, at the end, Q, in this case, 1, 2 is equal to 18.1 minus 5.4 is equal to 12.7 Newton millimeter to be fully correct. So answer the question. We have 7 minutes, so let's keep the multi-section shear flow for the next lecture. We'll probably take also a full lecture on just doing that. And then once we did that, I'm going to revisit the schedule, see how many lectures we have when we want to do the exam. Probably going to be a take-home exam as well, but when we want to do it. And based on that, I think we have to drop maybe one topic, and then we choose which topic we're going to drop. Okay, are there any questions? Nope. Okay, just another reminder, keep doing the book problems. They will help you a lot. Maxine has all the solutions. Like I said, this was, sometimes he's weird about it. Contact me if you don't understand it. But especially this course, there's a high correlation between practicing and getting it great. The more you practice, the more easier for you is to notice stuff like, okay, this is a symmetric problem. If I make a cut here, this will 0, therefore this will be 0. If I calculate 3, 4, by definition, I don't have to calculate 5, 6, and 7, 1, or 7, 8 if I calculate 1, 2. So stuff like that, especially when you have a time-limited exam, even 2 hour, 3 hour, these small steps can add up easily to 10, 15 minutes over one problem. If you just, instead of calculating everything, if you see that you don't have to calculate it. Another thing we didn't calculate is the central location, because we're not interested in that. We noticed that the moment of inertia is only dependent on Ixx, which is dependent only on Y. And here, it's only also dependent on Y, so we're not interested in the moment and the central location with respect to the x-axis. We're not interested in that. We know by definition we'll lie in the plane of symmetry, so we know this like in the middle. So we know if this is 200, this distance from 1 to the central axis, from 3 to the central axis is half of that is 100. So simple things like those become more easy for you to recognize when you do a lot of book problems. Okay? Okay. If there's no other questions, you know where to find me. You can contact me, and then we continue this Thursday. Thank you.